Hi everyone, this is Pengsi. Today I'll be talking about Antarctic slope undercurrent and onshore heat transport driven by meltwater upwelling. This work has been done in collaboration with my advisor in Stewart at UCLA, Alessandro Silvano and Alberto Naveira Garabato from the University of Southampton. The volume loss of the West Antarctic ice shelves is accelerating, with the most rapid ice shelf thinning detected in the Amazon Sea. In this region, elevated ice shelf melt rates have been attributed to transport of warm mid-depth waters onto the continental shelf. Near the Antarctic margins, both wind stress and tides drive the slope current to the west. Counterintuitively, observations and modeling studies have found eastward undercurrents along the shelf break of West Antarctica. The undercurrents are very important in driving basal melt because when encountering submarine troughs, they transport warm mid-depth waters directly toward ice shelf cavities. Using the original model, Silvano et al. 2022 have suggested that the melt rates of Amazon Sea ice shelves co-vary with the undercurrent strengths. In spite of the importance in driving basal melt, the mechanism of undercurrent formation is still unknown. In this study, we investigate the dynamics of the undercurrent using a high-resolution process model with coupled ocean, sea ice, and ice shelf. The model is forced by fixed surface air conditions that are representative of the annual mean state of the Amazon Sea. We restore ocean temperature, salinity, velocity, and sea ice properties at the zonal boundaries and northern boundary within a sponge layer. The undercurrents appear upstream of the trough with realistic strengths, which is very consistent with observations. The undercurrent is stronger upstream and significantly weakened downstream of the trough, suggesting a net onshore flow within the trough. Note that we only prescribe westward velocity at the zonal boundaries. In other words, the formation of the eastward undercurrent is not in any way imposed by the boundary conditions. We conducted perturbation simulations with varied winds, tides, diapycnal diffusivity, bedrock elevation of the continental shelf, and width of the trough. We additionally run simulation with a deeper thermocline or no trough over the shelf. There is a correlation between the undercurrent transport and ice shelf melt. Since winds and tides exert forces that opposes the undercurrent, this correlation between the undercurrent and ice shelf melt raises the hypothesis that the undercurrent is driven by sub-ice shelf buoyancy fluxes. To evaluate this hypothesis and provide insight into how basal melt influences slope shelf circulation and shoreward heat transport, we designed 4 controlled experiments with a pseudo-ice shelf. In these experiments, we turn off ice shelf thermodynamics and prescribe heat and salt fluxes at the tilted interface between the ice shelf and the ocean to create equivalent melt rates of 0, 8, 16, and 24 meters per year. This figure shows that increased meltwater flux drives stronger shoreward heat transport in the trough and enhanced cumulative heat transport at the ice shelf front. By analyzing the vorticity budget, we established a theory of undercurrent formation, and we also examined the theory across a wide range of parameters. Please check my longer talk if you are interested in this theory. The simplified explanation is that as the warm mid-depth waters melt the ice shelf, the upwelling of the meltwater induces clockwise rotation of the fluid via Earth's Coriolis force, and thus steers warm water clockwise into the trough at the shelf break, driving an eastward undercurrent. Here are the take-home messages. The undercurrent forms with realistic strengths, provided that there is a trough allowing access to the continental shelf and ice shelf cavity, and that there is a cross-slope buoyancy gradient. The bathymetric steering of the undercurrent toward the ice shelf is related to the clockwise vorticity input associated with diapycnal upwelling in the ice shelf cavity. This study implies a positive feedback for future climate change. Increased basal melt of ice shelves leads to a strengthening of the undercurrent, which increases shoreward heat transport, causing further melt of ice shelves. Thank you.